When the news got round, and as it was published in Nature, every physicist who was working in nuclear physics was just sick. It was a discovery that was overripe. All you had to do was walk into your laboratory, pull down some equipment off the shelf, set it up, and boom, there it was. You could see it. It would cause a big reaction on your meters. I talked to Glenn Seaborg, who was later to be the discoverer of plutonium, and he said, I walked around Berkeley for 2 days after that in a black fog.
Hello, and welcome to My Nuclear Life. I'm Shelly Lesher. Today on the show, I'm speaking to Richard Rhodes, Pulitzer Prize-winning author of the book, Making of the Atomic Bomb. I really couldn't think of anyone I would rather discuss the entirety of this topic with than Dick. His book was my first exposure to the history of nuclear science and impacted my personal journey into pursuing it as a career. If you have not read his book, use the link in the show notes and order a copy now. You won't regret it. Not only is Richard Rhodes a world-class historian and writer, but he has spent time interviewing many of the scientists involved in the Manhattan Project and was alive during World War II. Therefore, our discussion includes some of his firsthand accounts. It was impossible to include the full conversation into one episode, so I've broken it up into 3. In this episode, we discuss the beginning of nuclear science as a field until the Manhattan Project was approved. In part 2, we discuss the building of the project infrastructure until the scientists arrive at Los Alamos. Finally, in part 3, we discuss building the bomb and the end of the war. In order to tell the story of the Manhattan Project, we have to begin at the turn of the last century. William Rankine discovered X-rays in 1895, and shortly after, Marie and Pierre Curie discovered natural radioactive materials. So nuclear science was new. In 1911, Ernest Rutherford proposed a new theory of the atomic nucleus, changing everything. There was unbound enthusiasm in the scientific community around radioactivity and nuclear science. Discoveries were coming fast, but they were challenging some long-held beliefs.
Nuclear physics was still a new science, and it was still limited by the fact that no one had figured out a way to get into the nucleus, to look into the nucleus without having to bombard it with high-energy particles. Until 1933, one of the major turning points of this whole story, when the neutron was discovered. And the neutron, because it was the neutral particle, could slip right into the nucleus without being repelled by the nucleus's positive charge. Isidore Rabi, one of the great physicists of this story, said it was that if a neutron slipped into a nucleus at room temperature energy, it was as disturbing as if the moon had struck the earth. And then suddenly it became possible, as I think Enrico Fermi, the Italian physicist, first worked out, to start using the neutron to see what would happen when you bombarded various chemical elements. Fermi had a team going with him in Rome, and they worked their way through the entire periodic table, bombarding things. Once they had discovered, and this was a crucial discovery as well, that you needed to slow the neutrons down in order to get them to, they're released at pretty high energy in the various ways that neutrons are made. And Fermi was working uniquely in Rome with marble tables rather than metal tables. And on the marble tables, he got a lot more activity out of his bombardments than on the metal tables. The marble being a lighter material, lighter in terms of its chemical composition, slowed the neutrons down accordingly. The metal table just bounced them off, I suppose. In any case, once he discovered that slow neutrons were even better for exploring the nucleus, they worked their way through the periodic table. And really, in 1934, would have discovered nuclear fission, except that they were looking for transuranic elements when they were bombarding the large, heavier nuclei up in the 90s on the periodic table. And to prevent all sorts of scattering effects that they didn't want, that were getting in the way of their measurements, he wrapped his source in foil. And the foil prevented the fission particles from getting out. And several of the scientists who were working there at that time, that it was really quite fortuitous, because in 1934, Italy was under fascist government with Mussolini. Mussolini had various connections with Nazi Germany. And we probably would have had a German atomic bomb years before anyone else got it going. I mean, the United States didn't really get going till it entered the war in 1941. So it was lucky. When Szilard heard about the discovery of the neutron, he had been wondering if there was a way to cause fission in uranium or in some element. He didn't think of uranium. He actually thought of the other end of the periodic table first. But when he heard about the neutron, he immediately realized that here was the possibility of fission. He hadn't thought it all the way through. He hadn't thought of which elements might fission, but at least the basic idea was there in the mid-1930s.
There's a couple of things you said that I want to go back to. One is Robbie spoke about the moon hitting the Earth, like that's the way he described the neutron going into the nucleus?
Yeah, in terms of the amount of perturbation that it would cause.
That's a very kind of visual.
Yeah.
And it reminds me of Rutherford speaking about how when Rutherford came up with his model of the atom, and he spoke about how the alpha particle bouncing off the nucleus was as if a 15-inch shell bounced off a piece of tissue paper?
Yes, exactly. And in fact, there's an important thing to know about this time before the discovery of the neutron. The three leading scientists of the age, Bohr, Rutherford, and Einstein, all said at one time or another, the possibility of getting energy out of the nuclei of atoms is just moonshine. Moonshine was Rutherford's word for it, meaning, of course, ridiculous. You can never do that. There's no way you could do that. And the reason they thought that was twofold. One, because they were only using charged particles. And the best you've been able to, Rutherford, for example, had been able to do was to knock a little bit off of a compound nucleus. And two, the model for the nucleus was as if it were a hard ball, a ball of iron or a ball of stone. Really, it was not until Niels Bohr in the later 30s, continuing this investigation, began to think of the nucleus as a liquid drop, particularly when you get up to the very top end of the periodic table with uranium. Why is uranium the last natural element? And the answer is because it's just barely holding itself together. The various forces that are competing inside the nucleus are just at the end of their stability stage, and the next element up is an artificial element, neptunium and then plutonium. They don't exist in nature normally because they're not sufficiently stable. So the image of the moon striking the Earth is particularly apposite when we're talking about uranium. There, all it took was just the slightest slipping into the nucleus of a neutron for the uranium to fission. But this was all kind of tied up. Again, the visual aspect that you raised the question about. People visualized these phenomena in terms of real objects. And if you had the wrong real object in your mental picture, it could interfere with the way you thought about the whole thing, and it did. The real reason, as far as I could tell, looking at historical record, why nuclear fission was not discovered until late 38, and then by chemists rather than physicists, was because everybody thought that the nucleus was such a hard little thing that you couldn't make it split up.
But then something happened. In Nazi-controlled Germany, at the Kaiser Wilhelm Institute in Berlin, Fritz Strassmann and Otto Hahn were working at shooting neutrons into a solution of uranium nitrate.
They discovered, to their total bafflement, that they had krypton. They found barium in their solution, barium, which is about half the atomic weight of uranium. And they were baffled. What the hell was barium doing there? They had maybe expected they'd find something down in the 90s on the periodic table. Maybe they chipped off a little corner. But barium, they were totally surprised.
In a speech delivered to the University of California at Berkeley in 1955, Otto Hahn explains this discovery.
We made precipitations, Strassmann and myself, where we could be absolutely sure that there could be nothing else but either radium or barium.
Hahn continues his story as doubt starts to sink in.
Therefore, we could conclude that the substances could be really only radium, because barium was prohibited by the physicists. That we didn't dare to think at barium in those times. We always tried to explain what is wrong in our experiments. Not to say we will have barium, but we always thought it can't be there, and therefore we have to say what is the nonsense we are doing. It is so. The poor chemists, is it the same with you? The poor chemists? We are so afraid of these physics people.
These quotes by Hahn, and later by Otto Frisch, were from the Discovery of Fission exhibit at the American Institute of Physics webpage. Their Neil Bohr library has a large collection of audio files and oral history interviews, some of which can be found online.
Unfortunately, their resident theoretical physicist, Lisa Meitner, who had been working with them, had become subject to the Nazi anti-Jewish laws when Hitler annexed Austria in 1937. So she had to leave. She'd been able to keep her job in Berlin with these two chemists, but she'd had to leave under rather frightening circumstances. Get out of the country before the Gestapo arrived, if you will. And she had gone to Sweden, where she'd been not exactly welcome, but accepted into a laboratory there. But they wrote her a letter saying, we found this strange phenomenon. There's barium in our solution we don't understand. And she was vacationing with her nephew, also a theoretical physicist, Otto Frisch. And in a little village in western Sweden that I visited when I was researching my book, they went for a walk in the woods. It was a snowy morning, and talked about it all and thought, how would you get barium? And then realized that had to mean that the nucleus had somehow split almost in half. The other half would have been krypton, which was subsequently identified as part of the fission reaction as well.
Otto Frisch takes up on the story from a spring meeting of the American Physical Society in 1967, where he gave a talk, Fission, How It All Began, also from the AIP archives.
Lise Meitner was in Sweden and was lonely, so I offered to come and visit her, and we met in the west of Sweden, in a small place near Göteborg. And when I came, she was brooding over a letter of Hahn. And then we sort of kept rolling this thing around and saying, barium, I don't believe it, there's some mistake. You couldn't chip 100 particles off a nucleus in one blow. It's fantastic. It's quite impossible for a single neutron to do that. And I still don't know how we got to the concept of fission, but I remember Lise Meitner drawing a dotted circle on a piece of paper and saying, couldn't it be this sort of thing? Now, she always rather suffered from an inability to visualize things in 3 dimensions, whereas I had that ability quite well. And I had, in fact, apparently come around to the same idea, and I drew a shape like a circle squashed in at 2 opposite points. And Lise Meitner then said, well, yes, that is what I mean. Apparently she had, so to say, looked at the nucleus from the poles on, and with the dotted line was indicating the equator being pushed inward.
Then they started thinking about something they had learned from Niels Bohr, which was the liquid drop model. Think of a water-filled balloon. That's the way it behaved. And hit by a neutron, it wobbled back and forth and took various kind of wobbly forms until at one point it formed a kind of a dumbbell. And then the forces within the two nuclei, which were still connected, tended to push them apart until the neck of the dumbbell split and they pulled apart as two smaller particles. Once they had that vision in mind, they immediately saw how this could work. And they calculated the energy using the classic E equals mc squared, and were just floored by the amount of energy that this, the neutron was room temperature. It was carrying a few hundred electron volts, and suddenly you were getting this huge explosion out of so much, as Frisch later wrote, that one fission was sufficient energy to cause a visible grain of sand to visibly jump. And that's a lot of energy from one atom. So they realized, and Meitner wrote back to her friends in Germany, Hahn and Schlossmann, and she then, with Frisch, published a paper in the British journal Nature describing the physical aspects of the reaction. The two chemists published their paper about the chemical aspects in the German journal Naturwissenschaften. And the news was out.
How was this news received by the scientific community?
When the news got round, and as it was published in Nature, every physicist who was working in nuclear physics was just sick. Because, as one of these guys told me later, it was a discovery that was overripe. All you had to do was walk into your laboratory, pull down some equipment off the shelf, set it up, and boom, there it was. You could see it. It would cause a big reaction on your meters. I talked to Glenn Seaborg, who was later to be the discoverer of plutonium, and he said, I walked around Berkeley for 2 days after that in a black fog. Seaborg was an extremely ambitious man. He wanted to win a Nobel. He won a Nobel for plutonium for his discovery of an element, one of the easy ways to get a Nobel, except the elements are pretty much all gone now, I'm afraid. In any case, he was just sick with frustration at having not been able to make what was, after the fact, such an obvious discovery. And so was everyone else. So it really was an example of how in physics, in science, you have to have your model right in order to make that leap of faith that takes you from not having discovered something to discovering something. Really very interesting.
And you also have to not be afraid of kind of what other people are going to say. Because if you have this different model that goes against what everyone else thinks, then you have to have the
confidence,
the evidence, but also the confidence to come forward and say, look, I'm challenging that model that you have.
Yes, and usually that, as I've discovered in writing about other aspects of science, usually that's a long, hard process. It took Luis Alvarez and his son years to get the geology community to accept the idea that there was an asteroid impact that wiped out the dinosaurs. They just weren't prepared to believe in catastrophic geology. It was too biblical for them. And Louis was confident because he'd seen the evidence, but it was a long, slow slog. But here, exactly because anyone could pull it off on the lab bench, the demonstration was immediate and convincing and frustrating, but there it was. And someone said, just again, to think about how all these things work. Robert Oppenheimer, a central figure, of course, in this whole story. Within a week, Phil Morrison, one of his students and later a physicist of some renown, told me within a week, Robert had on the blackboard a drawing, Morrison said, a very bad and execrable drawing of a bomb. So the fact that this enormous energy was coming off this small reaction was immediately apparent to everybody. And although they had not yet proven that a chain reaction would occur, it seemed probable to enough people that the prospects of what could follow, meaning nuclear power and a terrible new weapon of war, were all there in the offing immediately to anyone who really did the numbers. It was a matter of doing the numbers. Again, something that scientists are quite good at usually, and in this case, it helped them see from the very beginning what a world-changing phenomenon this was going to be. So by the time Bohr then was scheduled to come to Washington for a conference on the 25th of January at the Carnegie Institution in Washington, D.C., and he, being Bohr, was telling everybody about this new discovery. Nobody had even thought about keeping it secret yet. In fact, it was soon all over the newspapers. You can find a headline in the New York Times, Fission discovered, and so forth. Possibility of 1 cup of matter powering the Queen Mary across the Atlantic and back, things like that, which people had been writing about for years, but it had all been hot air before. Now suddenly there was really something that might lead to such a phenomenon. So Bohr took the news to Washington, and again, I talked with some of the guys who were there at the time. They immediately ran over to the Carnegie Institution's laboratory where they had a cyclotron set up, and there was a pit below the cyclotron that reminded me of a kiva, of an Indian kiva down in New Mexico. And down there, they went to screen out anything else, and they ran the experiment and saw the particles. And that was the first time nuclear fission was demonstrated in the United States. So Bohr then, after he was at this meeting in Washington, went to the Institute for Advanced Study in Princeton, New Jersey, and worked there through the spring with a young physicist, American physicist named John Wheeler. And Wheeler, who was a theoretical physicist, and Bohr worked out what part of natural uranium was fissioning in this reaction. They realized pretty quickly that it wasn't the large isotope, the one that composed most of natural uranium, which was uranium-238. That doesn't fission except in special circumstances, and it doesn't chain react at all. But rather was a very small isotopic component of natural uranium, uranium-235, which, because of its particular nuclear structure, was something that would both fission and probably chain react.
And so most of this work was going on in Europe. Is that where kind of the hub of science was at the time?
It had been, although it was rapidly shifting. When Robert Oppenheimer came back from studying under the greats in Göttingen and Copenhagen, he began what had been backwater physics, began to teach the new quantum physics, to teach the new nuclear physics was moving along, because that was experimental physics. And we had a lot of good experimental physicists around, not a lot of good theorists at the time. But Oppenheimer opened basically a school at Berkeley and a school at Caltech. He taught half a year at each place, and students coming in from everywhere to work with him. I mean, and literally, because it was the Depression, Phil Morrison told me that he was living on cat food. Cat food, if you can imagine, but that was the cheapest stuff in the store. In any case, once the news got out, it just filled the newspapers and filled the headlines. All sorts of experiments were going on. One of the first things that had to be worked out was, would there be a chain reaction? And I think that came within the year. An experiment was done on a lab bench level where you could see fission. Well, actually, Fermi by then had come to the United States and was a professor at Columbia. And so had Szilard, although Szilard, as usual, was kind of wandering around on his own. But he got a temporary position at Columbia. And he and Fermi worked on to see if you get neutron multiplication from fission. And what they built was a tank of water with cans of uranium oxide stacked around in a kind of when you see an image of this object, this experiment, it looks like an early version of nuclear reactor. And in a sense it was. So they put a neutron source in the center of this cylindrical tank of water. And then they put these cans of uranium oxide, spaced them equally around it to give the water time to slow down the neutrons. And then they pulled the can and checked the material, and they found neutron multiplication. They found that the secondary neutrons had been released by the uranium in the uranium oxide. And that meant to them that there was the real possibility that you could get something that had previously existed only in chemistry, a so-called chain reaction, where one thing bounced off another and led to, in this case, the production of at least 2 neutrons for each original particle, which 2 would then split a couple more atoms and produce 4, and then you get, obviously, an exponential chain of reactions. They didn't have enough material, of course, in their assembly to come even close to actually having a chain reaction, or they would have blown up New York. But they were aware that was, at least I hope they were aware. So things got started.
It sounds like they moved really fast then. As soon as fission's discovered and it's announced, then experiments start, and it moves quite quickly at that point.
Yes, but only as science. No one in the United States, really, that I know of had thought, Oppenheimer had thought, well, you could build a bomb, but that was just Oppenheimer looking at the possibilities. We were not at war in this country. The war started in Europe 9 months after the discovery of nuclear fission in Nazi Germany. And that meant the British were keenly concerned once they knew what was going on. They were very much aware that although some of the best physicists in Europe who were Jews had to leave and had either settled in England or Ireland or other places, or most notably in the United States, which took a lot of them, that there were plenty left in Nazi Germany, including Werner Heisenberg, one of the great physicists in quantum physics, and any number of others. So the British quickly realized that there could be a real problem and started thinking about it. Although even then, I have to say, it really didn't get very far until 2 of the Jewish escapees, Otto Frisch again, who by now was at Birmingham in England, and another Jewish physicist named Rudi Peierls. Peierls and Frisch were sitting around talking about all of this when they kind of idly wondered what a critical mass would be. No one had really thought to the point of thinking, well, how much uranium would you have to put together in one place to make a bomb? And they hadn't really got to the point where they even thought, what isotope of uranium would you need? They were just thinking in a very general way. And they started doing some calculations, and they came up with maybe no more than 1 kilogram, a little ball, the size of a golf ball. And at that point, even though that was just a bare order of magnitude estimate, they then said, well, how much would it cost to make that much? When Szilard arrived in New York and began working with Fermi, they were both curious to see if indeed you could make a reactor, basically. And that's when they did this experiment using a tank of water and some cans of uranium oxide. And they did find secondary neutrons produced in the reaction. And that told them that perhaps, wasn't for sure yet, but perhaps under the right circumstances, you could arrange a mass even of natural uranium in such a way that you could produce a chain reaction. When the war began, then the following September 1st, 1939, with the Nazi German invasion of Poland, the United States was not much changed by that. But Great Britain indeed was, because very soon Germany was attacking England. The famous Blitz, when there were flying planes over London and bombing and so forth, was all going on and was a very near thing, in fact, in the end of 39, beginning of 1940, and into 1940. So the British had more reason to be interested and concerned in the possible development of a weapon, and particularly when Frisch and Peierls worked out the probability that it would not take a huge amount of material. They figured that you could probably separate U-235 from U-238 in a factory that wouldn't cost more than a battleship. That's the way they framed it in their minds. It did, in fact, cost more than a battleship.
Substantially more than a battleship, in fact.
They were still working at an order of magnitude level. So they wrote up a paper about it, a very prescient paper. It's in the back of one of my books, and it's really quite impressive to read so far away now from that time with so little real knowledge in hand. But they wrote up actually two papers, one that discussed the actual physics of the problem, and the other that discussed how you would go about making this material and how you would go about exploding it, for that matter. Everyone saw pretty quickly that if you had the right kind of material, all you'd have to do to make it explode would be to assemble what was called a critical mass, which was a large enough volume of the material that enough neutrons bounced around inside without escaping that they started and sustained a chain reaction. And it turned out for highly enriched uranium, natural uranium enriched to above 90% U-235, when its natural U-235 content is only 0.7%. So there's a huge transformation involved in moving that small amount of isotope, adding it and adding it and adding it until you finally have more than 90% U-235. That all you'd have to do is put together a sphere about 125 pounds of the material. And since uranium is the heaviest element, natural element in the world, twice as dense as lead, that would be a ball about the size of, let's say, a soccer ball, or actually less than that. So they just simply visualize a gun with one piece mounted on the muzzle and another piece fired up the barrel like a bullet. And when the two pieces came together, that would form a critical mass and the whole thing would blow up. It was a little more complicated than that, but surprisingly not very much. There was even a joke that went around the common room at Cambridge at those days, once they figured out the idea of a critical mass, which was you'd get a critical mass of U-235 in little cube form. And you'd send these cubes in little gift boxes, one at a time, to Adolf Hitler. And when they were all assembled on his desk, then it would blow up and that would take care of that.
Oh, wow. So two things. One is their idea of kind of this gun barrel is exactly what happened with the little boy device.
That's correct. Yeah.
And the other is there were German uranium cubes that were found after the war.
Yeah. Well, that was actually part of a German reactor that was designed to use a very special kind of isotope of water, of H2O, called heavy water, which is enriched in deuterium, an isotope of hydrogen, and which makes it capable of forming a chain reaction with ordinary natural uranium. So those were small cubes of natural uranium encased in, I think, zirconium or some metal to keep the uranium from reacting with the water, hanging on chains in a tank of water. It was a very elegant design for a reactor, but by the end of the war, the Germans had only gotten to a half-sized reactor. They hadn't built a full-scale reactor yet. That's how far they got off track along the way. So we go back to the beginning of the war.
Yeah, sorry, I got you off track there, but that's what the little cubes made me think of.
But the heavy water is of relevance because Fermi quickly, once he saw from his water tank experiment that you could get neutron multiplication from uranium. Then he started thinking, well, ordinary water won't work. He did the calculations and realized that water absorbs too many neutrons. You couldn't, using natural uranium, build a reactor. You just wouldn't get there. So what other material is the light element that he could use that would be more workable than heavy water, which was normally produced in gram quantities at great expense at a huge, huge electrical plant in Norway by Norsk Hydro. They were the only producers of the stuff because it was so hard to make. It took so much electricity to basically hydrolyze water and pull off the heavy water part and do it again and do it again and do it again, multiplying the enrichment at each stage until you have something that's almost all heavy water. So what else could he use? And he pretty quickly realized he could use graphite, which is a light element, and would do the same thing, bounce the neutrons around in basically a billiard ball kind of phenomenon, bouncing neutrons around. And each time they bounce, they'd lose a little energy and slow down. And slowing down would make them more capable of penetrating the nuclei of the uranium in the arrangement. So once he realized that graphite would work, that's the way he started building what were called exponential reactors, small ones to start with, and then he kept adding scale as he got more material. These blocks of graphite were light elements, but they weren't light. So he enlisted the Columbia football team, hired them to handle these blocks of graphite for him, and they made extra money in their spare afternoons building a series of increasingly large exponential reactors. And he would measure the neutron multiplication each time and then add some more and add some more.
I have this image in your book of scientists or football players building this reactor wearing like furs that they found in a...
That's a little later.
Oh, okay.
Basically, it follows from the ones that he was building at Columbia in New York. But before we go there, the Germans, Heisenberg and his group, realized that graphite might enable them to do exactly what Fermi had worked out. But they didn't understand they had to have very pure graphite. Ordinary industrial graphite has some impurities in it that absorb neutrons. And in order for Fermi's graphite to work, he had Szilard, again, this fascinating gadfly of a guy, going around to the graphite companies insisting on greater purity in their graphite. They'd never made such graphite before. They couldn't understand why anybody would need graphite that was purified to such a high level. But he was paying the bills, so they made it. So we got past that particular potential tripping point. But the Germans didn't. They had set graphite aside and said, it won't work. The only thing that will work is heavy water. So they started collecting together heavy water. And when the word reached Norway, this happened fairly early in the war. When the word reached Norway that the Germans were coming after the supply of heavy water that had been manufactured at Norsk Hydro, some guerrillas for the Norwegian military, under the guidance of the British secret force, blew up the heavy water plant attached to this giant dam at Norsk Hydro. One of the stories that I love about it is that the mayor of the local town, who had been coordinating a lot of this activity, in order to have an absolutely foolproof alibi when the Gestapo came around to find out who had caused this terrible thing to happen, arranged to have his appendix removed that weekend. It was not sick. There was no problem. And this was in the days before antibiotics. I mean, what a brave thing to do. And what an unassailable alibi he had.
Wow.
In any case, they blew up the Norsk Hydro plant. And then the last casks of heavy water, which the Germans had already confiscated, were being shipped across a lake, I think in Sweden. And even though there were civilians on this ferry boat, they sunk the boat. They killed some civilians in the process, but they made sure that that heavy water never reached Germany. The Germans were hamstrung throughout the war by this misunderstanding about what sort of material they could use to make a reactor. And you had to make a reactor in order to prove the chain reaction. And also because by then Glenn Seaborg had discovered plutonium as a product of bombarding uranium-238, the waste material in the uranium, in natural uranium, the stuff that poisoned the chain reaction and had to be removed in order to make a bomb. Suddenly there was a way to make a bomb using U-238 by bombarding it with neutrons, producing first neptunium, which is 239 neptunium, and then it decays in about 4 days into plutonium-239. And plutonium is about twice as reactive as U-235. Critical mass of plutonium in a spherical form with a tamper around it is only 6 kilograms, about the size of a baseball.
So where are we in our timeline?
Now we're around in 1940-ish. British are at work. The papers that were written by Frisch and Peierls have gone to their boss in Birmingham, who's part of a government committee called the Maud Committee, to discuss whether there's anything you can do to use this new reaction in war. And when these papers arrived, the Maud Committee says, bingo, there it is. They've worked it all out. And just to jump over again to Germany, one of the big mistakes that they made, as well as missing graphite, was that Heisenberg, one of the great mathematical physicists of the century, unaccountably never figured out the critical mass of pure uranium, of U-235. He thought it was going to be several tons. In other words, he was thinking in terms of a reactor rather than a bomb. He hadn't made the mental leap to the pure U-235 system and how that would change things. In any case, Frisch and Peierls' memorandum went to the British government. British government realized immediately how important it was, and then had a discussion about whether they could do this themselves or whether they would have to engage the Americans, who, of course, were not yet at war. Some of the British scientists were prepared to go down to their death, not letting the United States build the bomb. But they understood that they were being bombed by Germany. They might be invaded by Germany. There was the possibility, they thought, of building the machinery to enrich uranium, which would take vast factories because it was such a difficult problem in Canada. But Canada was not really industrially rich state either. So they began to think, how can we get the Americans involved? In the meantime, the whole notion that there were war possibilities for uranium had finally sunk in. Fermi had a debate with Szilard about whether they should go secret, and he didn't want to. He thought that that was a violation of everything science was about. And Szilard said, look, the Germans have to be working on this. We can't share this with them. But eventually Fermi reluctantly agreed. And all of a sudden, all the nuclear physicists weren't publishing papers anymore. And although the Germans don't seem to have made much of that, there was a Russian scientist named Georgy Flyrov. And Flyrov noticed that all the nuclear physicists had stopped publishing papers in public journals and wrote a letter to Stalin saying they're working on a bomb. They have to be. Why would they go secret otherwise?
So this was in the early 40s?
Yeah, this was just barely 1940, maybe late 39. I mean, just at the outset.
So how did they let each other know what they were doing then if they weren't publishing in journals?
Well, they were still talking to each other. They just weren't publishing, just weren't making all this public. I mean, they talked to each other throughout the war. Einstein was never given a security clearance during the Second World War. Our government was afraid he'd go pacifist on them and spill beans. But he knew all that was going on because people would stop in at the Institute for Advanced Study and say, hey, Al, let's have lunch. Let me tell you what I'm doing. So there was always this informal process of communication among the scientists. Even though the bomb was a really well-kept secret throughout the war.
So perhaps they didn't take their security clearance very seriously when it came to speaking to each other about what they should and should not talk about, but they took it seriously when it came to talking to outsiders about it.
Well, as soon as they began working with the United States government, and particularly as soon as the Army Corps of Engineers was assigned to run what then became the Manhattan Project, because the original office had been in Manhattan, as simple as that. General Leslie Richard Groves, Dick Groves, clamped down a form of security called compartmentalization, which was pretty much the standard way security worked at that time. And that was, you were only allowed to discuss the specific work you were doing, and then only with the people who were directly working with you. So if I was working on, let's say, helping build a reactor in New York, and there was someone at Berkeley working on studying the chain reaction, and we couldn't communicate with each other.
But that doesn't seem very effective.
Well, no. I mean, for science operates by gift exchange. Science operates by scientists sharing their discoveries with each other, and thereby keeping the moving cutting edge of science moving forward. I learned from you, you learned from me, that gives me an idea, that gives you an idea. We try them out, and then we share that, and forward we go.
Absolutely.
That's the way science is supposed to work. It doesn't always work that way. But if it didn't work that way, it would stop, because the cutting edge is where the new discoveries are made. And if people kept all that secret or just patented it and put it away, then you wouldn't be able to make any progress.
So I'm guessing the scientists didn't follow his rules.
Well, Oppenheimer once said that we didn't do any physics from 1939 to 1945. And although, of course, that's not true, what he meant was an awful lot of the problems connected to making a bomb were basically high-level engineering and chemistry. Not about the only really new things that were done, for example, at Los Alamos later in the war, was measuring cross-sections for various reactions. Other than that, it was a really fancy engineering problem. And in that sense, most of what was going on could be compartmentalized. Later on in the story, we'll see where that broke down and where it was deliberately set aside. But let's stay chronological here, I think.
All right.
So then the British problem was, how do we get the United States involved? They've got the money, they've got the space, they're spared the bombing problem. How do we get them involved? And it wasn't easy. Our scientists were skeptical, first of all, whether this would even be possible. There was a decision made by the Maud Committee and the British government to give to the United States at no charge all of their best World War II military secrets, most particularly the microwave tube, which they had invented, which made radar possible, because it amplified energy, radio energy, at such an enormous rate compared to vacuum tubes. So they had invented the microwave tube, and that and all their other best inventions were put in a big black Japan tinned metal suitcase or trunk and shipped over to the United States, along with a couple of leading British scientists, to explain what all these goodies were. And they shared these things around, and there still was not much action on nuclear weapons. So one of the British scientists went around to all the universities and talked to all the physicists he knew, Oppenheimer among them, and said, this is serious. There's a possibility of a bomb. We've got to beat the Germans to the bomb. You know, there's so much revisionist history about why the United States built atomic bombs that is pretty scurrilous, I think, that says basically, oh, those scientists could have kept this under their hats. They didn't have to tell these governments about this discovery, and then we wouldn't have had those terrible bombs to bomb those nice Japanese civilians. Well, no. If the day nuclear fission was announced, every physics laboratory in every country in the world that had physics laboratories started looking at this new reaction. That's how exciting it was. It was a major, major break. Well, the first new form of energy, major form of energy not dependent on sunlight. in the history of the world. Coal is dependent on sunlight, so is wood, and so forth. Gas.
So everyone was
working on it. The Joliot-Curies were working in Paris. Heisenberg and his people and Hahn and Strassmann were looking at it in Berlin. The British were looking at it in Birmingham and Cambridge, and on and on and on. The Russians were looking at it.
The Japanese were looking at it.
The Japanese put one of their military officers, who was an engineer, assigned him to follow the development and see where it might lead. And indeed, the Japanese started a bomb program early in the war, but very soon realized that the sheer amount of material they would need to enrich uranium. Let me just mention that because we've been talking about that. The only difference between U-235 and U-238 is a slight difference in mass. In every chemical way, they're identical. So how do you separate these things? You have to somehow turn the uranium into a gas, and then using various possible techniques, including electromagnetic isotope separation, that was one method. Gaseous diffusion, where one gas is slightly lighter than the other and diffuses a little faster through a membrane of some kind, a kind of screen. Another form that involved a heated column, which was called steam diffusion, where you had a cold pipe and a hot pipe, and the temperature difference separated the isotopes, but ever so slightly. So rather like oil refinery, and the factories were of that scale, you had to do it over and over again. You'd bleed off the slightly enriched in U-235 portion and run it again through another separator. And then you'd bleed off the enriched portion and run that through another separator. And there were hundreds of stages that this had to go through in order to enrich this material from 1 part in 140 to 90 parts out of 100. So it was inevitably going to cost a great deal of money to do that. And again, the discovery of plutonium by Glenn Seaborg in 1940, I believe, or 41, offered an alternative path to the bomb that would only involve building some large nuclear reactors, but only that meant you had to develop a supply of uranium, you had to develop a supply of highly purified graphite, you had to build these huge machines and make sure they didn't blow up, and on and on and on. So one of the Russian scientists said to me, when I interviewed them in the 90s after the fall of the Soviet Union, he said, scientists had to trust their government, and the government had to trust their scientists, because there were lots of steps between the discovery and the bomb, and they were going to cost a lot of money. And there was no guarantee at the other end that you would end up with what you hoped you'd end up with. And he said, in the United States, the scientists trusted their government and the government trusted their scientists. But in the Soviet Union, not so. Stalin, until Hiroshima, was pretty sure that this was all some kind of American disinformation campaign to get him to waste a lot of money that he didn't want to spend. It was only when word came to him of the explosion at Hiroshima that he finally started serious work on a bomb. Before that, they had a lot of laboratory work that they did, but they never got outside the lab. So something like that, in fact, happened in Nazi Germany. Hitler just really was not terribly interested in this new discovery. He didn't really envision it. He laughed about it. He said, oh, yeah, the scientists have always been on their way to blowing up the earth with their laboratories. He was much more excited by rockets. You could see a rocket. There it was, right in front of you. Boom, off it goes.
And it doesn't take that long to build a rocket, to see something.
Right. The principles were in hand. The only problem was that those rockets cost as much as bombers, and you could only use them once. So the joke in Great Britain when the V-2 rockets started landing in London was the Germans are using our best secret weapon, V-2 rockets, because they're basically throwing a bomber away every time they blow up one of these things. Whereas the British had bombers, and of course the United States had bombers that shuttled back and forth, dropping bombs and dropping bombs and dropping bombs. So the intercontinental ballistic missile, which is what those B-2 were, or intermediate range, but the same thing, really was of no use to anyone until you could put a nuclear weapon on their noses. Then suddenly they became what they now are. So all this was turning around. You can see how everyone was thinking. But again, I go back to this Frisch-Payerl's paper, because in the second of the two papers, they said something like this: we cannot think of any physical structure that could be proof against one of these explosions. Therefore, the only defense against such a weapon would be a similar weapon in our hands to threaten if they chose to use their weapon. In other words, deterrence. So deterrence as a concept was in place even before there were any bombs, much less means of delivery. And again, to go back to these people saying the scientists didn't have to build the bomb, we worked on the bomb, first of all, and until well into the war, until perhaps 1944, primarily because we were afraid Nazi Germany was going to get it first. And the idea, as someone said, of a Hitlerian Third Reich dominating the world for the next 1,000 years with nuclear weapons was horrifying. And let me just say how horrifying. I wrote a book about the Holocaust, and I looked at the documentation from the famous Wannsee conference when the decision was made to go ahead and murder all the Jews. The documents didn't just include the Jews of Germany and Europe. They included all the Jews in England when Germany, as it imagined, won the battle with England. They included all the Jews in America when Germany, as it imagined, won the battle with America, and on around the world. The total number of deaths that were projected in that document were 20 million deaths. That was what was in store for the world if Nazi Germany had got the bomb first before anybody else had it.
So the fear was justified.
The fear was totally justified, and it was only prudence. The problem still was, however, that until December 7th, 1941, a day that shall live in infamy, I remember I was 4 years old. I remember vividly how everybody started running around like chickens with their heads cut off when the news came that the Japanese had bombed Pearl Harbor. Until then, we just weren't in the war quite. So we did what we could, and what happened is the United States scientific community worked the problem up, checked this, checked that, measured this, measured that. And by October of 1941, had reached the point where they could reliably go to Franklin Roosevelt and say, this weapon is possible, and we should expend whatever we need to expend to make it happen. And Roosevelt signed off on it then. Then the scientists and the industrialists and others, this was before the Army was involved, got together again at the Carnegie Institution in Washington on, of all days, December 6th, 1941, and voted that they would go ahead with a full-scale industrial program, and then woke up the next morning to Pearl Harbor. So I guess they must have felt they probably made the right decision.
So the plan was to move forward before Pearl Harbor.
Yes. But I don't think anyone had really envisioned the scale yet. For that, you needed the Army Corps of Engineers.
Thank you for listening. We would love to hear from you, so send email to mynuclearlife@protonmail.com and would appreciate it if you rate, review, and subscribe on iTunes or wherever you listen to podcasts. A special thanks to Dick for being so very generous with his time, and Lexi Weghorn for all of her help with this podcast. Thank you for listening, and tune in next time when we will explore what resources it took for the U.S. to build the bomb. I'm Shelly Lesher, and this has been My Nuclear Life.